Our group decided to focus on the double slit experiment. The double slit experiment was first conducted in 1801 by polymath Thomas Young. In order to conduct his experiment, he utilized sunlight and two large, narrow double slits. Thomas Young wanted to prove whether light acted as a particle or a wave. Young's experiment became to be known as part of classical physics. Other researchers built upon this knowledge, and classical physics became what we now know to be quantum mechanics. The double slit experiment demonstrates the idea that light acts as a wave. These waves can be constructive or deconstructive when overlapping. This constructive and deconstructive interference can be observed as light and dark areas projected onto the wall. These light and dark bands should be equally spread apart. The dark areas correlate to destructive interference, whereas the light areas correlate to constructive interference. At the center should be the brightest point. As the bands become further from the center, the brightness should decrease. In order to complete our experiment, a 650 nanometer laser, a double slit disc, a 12-inch ruler, and a single piece of paper were used. The laser and screen were placed 1.5 meters away from a wall. The screen was set to the double slits with 0.25 millimeter spacing. The laser was then turned on and the interference pattern was observed and measured.
So as you can see here in this experiment, we have the 650 nanometer laser shining through the double slit here. And the double slit is exactly 1.5 meters away from this piece of paper. And this piece of paper, as you can see, has a ruler attached, and it measures up to millimeters on here. And as you can see here, as you rotate through the different types of double slits, you will notice that there are different interference patterns depending on the two variables.
Using a 0.04 wide millimeter double slit with 0.25 spacing, we were able to calculate that the distance between each band was 0.0039 meters. This, compared to the experimental value of 0.004 meters, means that our experiment was a success. What happens to the distance between the bands when the spacing between the slits is doubled? Here we have a 0.04 millimeter wide double slit with 0.5 millimeter spacing. We calculated that the distance between each band was 0.00195. This coincides with the experimental value of 0.002 meters. What this shows us is that when the distance between the slits is doubled, the distance between each band decreases by half. Does the distance between bands also double when the slit width is doubled? Doubling the slit width from 0.04 to 0.08 millimeters, we found that the distance between the bands was exactly the same as with the 0.04 millimeter wide double slit. Therefore, there is no observable difference that occurs when slit width is doubled. Our experiment was a success. We found that light acts as a wave, and those waves can be constructive or destructive when overlapping, with the light bands representing constructive interference and the dark bands representing destructive interference. We also found that the distance between the light bands is completely dependent on the light source wavelength, the spacing between the slits, and the distance between the source and the observed pattern. Furthermore, we found that changing the width of the slits seems to have no effect on the distance between the light bands. Thank you for watching.